Thank you for the introduction. And yeah, it's me again. I'm Yanzuo. And this time, I will talk about BitShield, defending against bit flip attacks on DNN executables. This is a joint work with Yuanyuan, Zhibo, Sihang, Tianxiang, and Wang. So as more aspects of our lives depend on AI, the consequences of insecure AI systems are also getting more serious. Your car may bring you to wrong places, you may lose your money, and in some extreme cases, you may also get accused of some weird crimes you didn't commit at all. So AI systems need to be secure. And we've seen so many types of attacks against them. Adversarial examples, backdoors, model stealing, there's really a lot. But these are like high-level, model-level attacks. And what do I mean by that? Well, in this talk, we're talking about a low-level, an infrastructure-level attack. More specifically, we're talking about bit flip attacks, or BFAs. So there are a kind of attack that flip bits in the memory or DRAM. And its most prominent instance is Rowhammer, a die-hard hardware bug that can be used to cause bit flips in the memory. And currently, researchers have also demonstrated this on basically every generation of memory models that we have. So BFAs on AI and ML systems are not new. Researchers have found that they can attack DNN models by flipping data bits in the model weights. So if you flip the bits in the model weights, you'll distort the weight data and subsequently the model predictions. This will make model do fun things like outputting incorrect classification results. However, we found that this is not the whole story because current research doesn't cover the case of DNN executables. But first, what are DNN executables? Well, they're a type of executables compiled from DNN models by deep learning compilers like TVM from Apache and Glow from Meta or Facebook. And people want them because of their performance. They're optimized at both the computational graph level, so the model becomes more efficient, and the target hardware platform level. So they kind of extract the maximum potential out of the hardware platform that they will be running on. And so essentially, DNN executables are compiled code which contains, for example, all the operators used by the original DNN model. And this makes them unique. This is also where you can see the current research overlooks a huge portion of attack surfaces because they only consider flips in model weights, but not in code. So our preliminary survey finds pervasive code-based bit flips attack surfaces in DNN executables. They allow single-bit corruption, meaning that just one flip is enough to significantly degrade the model accuracy. And that stays true even for quantized models, which have been considered more robust against BFAs. And on the defensive side, we found that the current defenses can't really protect DNN executables. For one thing, they only consider protecting the integrity of weights. And for the other, these defenses may also be bypassed by the flips that happen in code. So here's a simple example to show that. So in this example, we are showing the before and after comparison of a bit flip attack. So imagine there's some defense mechanism implemented somewhere after this snippet. So after the flip, the original computation instruction become here leave and return, which means that everything after this snippet will not be executed anymore. So the defense would be skipped or bypassed. So DNN executables suffer from both old and new bit flip attacks. And to defend against both of them, we believe there are these requirements for defenses. We want them to be unified and generic, obviously, so they work for not just one, but both types of attacks. And they need to be self-defending due to the possibility of bypassing that we just saw. We also want them to be applicable to different models and be performant, so they can be used in production environments. So how can we design a new defense that meets all these needs? One important realization we had was that we can model the attacks from the perspective of semantics. Essentially, so DNN predictions are a decision process based on the code logic and the model weights. And B-flip attacks, no matter they are weight-based or code-based, they can be seen as the processes to break those decision processes and to change the semantics of the model. But how should we capture the semantics of DNN models? Well, while tools like control flow graphs may work pretty well for like traditional programs, that's not the case for DNNs, because DNN semantics are like implicit and embedded in the computation process. So to solve that, we took inspiration from gradients. Because a randomly initialized models, its decision process can be trained into a useful one under the guidance of gradients, we can also represent that process during runtime by inversely measuring how the model's output could be turned back into a random guess. So more specifically, let's say we have the model output y. We prepare the vector u, which is of the same length of y, but with all elements equal to each other. This vector u will represent a random guess. And then we measure the distance between u and y using KL divergence. And finally, we can backpropagate this value to any individual model layer, so we can capture the semantics. And here we are also recording the normal semantics using the training data of the model, so we have a reference to compare with. And by implementing these semantics checks, we are achieving 92% mitigation rate for weight-based attacks. But obviously, this is not the end. We still have to deal with those code-based ones. So recall that code flips may allow defenses to be bypassed. That means semantics checks themselves may also get bypassed. So we need self-defense mechanisms to make sure our defense really works. And to accomplish that, we are taking inspirations from the avalanche effect from cryptography, where slight disturbances get artificially amplified significantly to make everything tamper evident. And in the context of our defense, we're going to fuse code checksums into the semantic calculation that we laid out earlier. So when the code flips happen, the code checksum will change, which will then cause the capture semantics to also change drastically and expose the attack. So more specifically, we do it through a pair of masking and unmasking operations. Let's say we represent our semantic capturing process computation with this equation, O equals to W times V. Well, it's simplified, but you get the idea. And we can rewrite the equation like this. So we surround the parameter W with a masking operation and then an unmasking operation. So these are a pair of inverse operations that work somewhat like encryption and decryption operations. They only cancel each other out if the same key is provided. So here we are plugging in the embedded checksum, which is calculated at compile time, and the runtime checksum, which is calculated dynamically as the keys. So if the code has been tampered, these two won't match and the operation won't cancel out. So the captured semantics would change drastically. Okay, last but not least, it's also desirable, we believe, to prevent potential damage early where possible. Because that would stop the propagation of errors caused by BFAs. So to do that, we add a checksum canary into our defense. It's created by inserting plain checksum checks into the model, and it will hold the model execution as soon as it spots a checksum mismatch. So that finishes our defense for both weights and code-based attacks. And we'll now go into evaluation. First, threat model and setup. So all our attackers are white box and adaptive, meaning that they know everything, including our defense, and will actively try to bypass it. So specifically, we have code-based attackers with these aggressive and stealthy strategies or profiles. And we also have a weights-based attacker from the existing state-of-the-art method. So we run the attacks on 5 profiles representing different DRAM platforms, which we obtain from existing surveys. Finally, we assess our defense on metrics including attack success rate, post-attack accuracy, and performance overhead. And here we consider an attack successful if they cause an accuracy drop of at least 3%, which should be representative enough. Time for the results. In terms of attack success rates, we are decreasing code-based attacks from 100% to 0, and weights-based attacks from 96% to 7%. And with our defense, attackers also no longer degrade models to a random guesser after the attack. While without the defense, they would have consistently succeeded. And finally, our defense only brings a performance overhead of about 2%, 2.47%, indicating its high practicality in production environments. So let me summarize those numbers a bit for better understanding. So our results says that we have mitigated all code-based attacks and 93% of weight-based ones. So we significantly decreased their ASR. And even if attackers still manage to succeed after the defense, their impact is now limited significantly. And finally, all of this comes with an overhead of just 2%. So in this talk, we introduced the unique bitflip attack surface on DNN Executables. We proposed a semantic-based defense to protect these old and also new kind of attacks. And our defense is highly effective with a low overhead. Thank you.
Yanzuo, we have time for one question.
So I would like to hear the setting of your adaptive attack, and I would like to you to provide more instinct of why the adaptive attack cannot bypass your defense.
Okay, thank you. So the adaptive attack is like, they're called adaptive because they know every detail of the defense, and they will try to, like, for example, check if, like, the first thing they check is that if we can skip those checksum checks altogether, if we could get enough bit flips to, like, rewrite the whole checksum or something like that. So we actually have an algorithm listed in our paper, but we're not showing that here for time. And what was your second question?
The reason, the intuitive, why the adaptive attack, why it's hard for the attacker to hide.
Yes, the instincts.
Yeah.
So basically, the instinct we are having here is related to the avalanche effect. So we are making it very difficult for the attacker to bypass these attacks. So theoretically, it's not impossible, but they would need to flip many bits that are distributed in the models. Well, for example, for more details, you would need to refer to our paper.
Sure.
Yeah. So the instinct here is that we are making it really difficult for them to succeed. Yeah.
Okay,
So-
thank you.
My question is quite quick. And the checksum function is a cryptographic checksum function because I don't think it's secure enough.
Okay, thank you for the question. So by secure enough, you mean...
Cryptographically secure, I mean that it looks, we can easily find out the collision pair, even though they are not the same before, even after the flipping attack. So in that case, attacker can easily
Okay.
bypass the defense.
Well, we are not using things like SHA-1 or SHA-250.
That is my question.
Yes, we are not using that because of
Then it's not
performance.
secure, right?
It is not, because what we are using now is Adler 32, and they have 4 bytes or 32 bits of entropy, which in the context of bit flip attacks makes it really difficult for the attackers to gather all these memory templates, which is a Rowhammer term, I think. So they would be really difficult to gather these resources to simultaneously flip those bits.
There might be many attacks actually in that case. Okay, thank you.
Okay, I suggest we take the more discussions offline. So let's thank Yanzuo one more time.